Hi there, I'm Stefan T. Lowitt, and welcome back to part 8 of my video introduction to the STL. I'm the Visual C++ Libraries developer who maintains the STL, working alongside Dinkumware. And today I'm here to talk to you about regular expressions. In parts 6 and 7, we looked at algorithms, and regular expressions are string algorithms. They are interesting because they are declarative. Instead of writing code that walks through string pointers or even string iterators and examines characters and has branches and sets flags and things like that, instead you describe the sort of string that you're looking for, and the regular expression machinery will then find an occurrence of that string and do something with it. Now, the great thing about regular expressions is that they can do so many things. If you've used other regular expression libraries or other languages, especially Perl, which works very closely with regular expressions, you're familiar with what they do. Of course, you can, match strings and search for strings, but as implemented in C++ OX and originally TR1, regular expressions in C++ can do a lot more things. In fact, there are even regular expression iterators, which are insanely powerful. We'll be seeing how they work. So here I've got one of my slides that explains all of the things that you can do with regular expressions. The simplest sort of thing is validation. If you're receiving user input, well, the first thing we know about users is that they love to type in garbage. We often want to validate whatever they're sending us to make sure it's not garbage and that it's well-formed. So we could make sure that maybe a username that they're entering is valid or conforms to some other pattern that we would like to describe. The second sort of thing we can do is if we've got a string that we know is valid, perhaps we would like to decide what set of strings it belongs to. For example, we could have a valid file name, but maybe we want to only look at its extension. Or we could have a name and want to look and see, okay, does this name have a middle name? Or does it have a middle initial? So you can decide what set of strings a particular string belongs to. You can also just take arbitrary input and parse it. For example, dates can come in a lot of forms, month, day, year, put the year first, put the year last, write the month out as words, put the month numerically. You can use regular expressions to describe the different parts of a string and do what I call crack it open, and look at the different components of that string and then go parse them as integers or substrings or whatever you like. Moving on to the more powerful things that regular expressions can do, they can also perform transformations. You can describe a pattern that you would like to find in a string and replace all occurrences of that pattern with something else. Maybe a fixed string, maybe parts of the pattern. This is enormously powerful. And then sort of the final two things you can do with regular expressions in C++ is use those regular expression iterators that I mentioned to either iterate through a string. So you describe a pattern like maybe a word or a number or a date and look for all of the occurrences of that pattern throughout the whole string. And this conforms to the iterator model that we've seen so much about. And you can also tokenize a string. If you have used the C standard library, you may be familiar with the function strtoke. That function is horrible for many reasons. It's very limited, difficult to use. It's full of gotchas. With regular expressions, you can tokenize strings in a much more powerful way, splitting on arbitrary white space or any expression that you like, and that's powered by regex token iterator. So if you'd like to know more, this slide is derived from one of my slide decks. If you just do a search on the interweb for TR1 slide decks, the first result should be one of my VC blog posts. If you go to the bottom of it, you'll see a zip file that contains this TR1 presentations.zip. It contains a regex talk that I gave a couple years ago. And this not only describes what you can do with regular expressions, but also contains a quick introduction to the regular expression grammar. If you've used regular expressions, you're probably familiar with things like star and plus, but you may not have seen things like non-greedy quantifiers, capture groups, non-capture groups, all the various things you can do with escapes, hexadecimal escapes, character class escapes, and all of that syntax I've crammed into this slide deck for your reference. So definitely take a look if you'd like a quick refresher on how regular expressions work. I'll assume that you've heard of them, you've maybe used them a little, but that you haven't used them in detail and that you haven't looked at how they're implemented in C++ yet. So let's take a look at some code. Here I've got code working in Visual Studio 2010, which I highly recommend that you use. Regular expressions were originally implemented in Visual Studio 2008 SP1. But it actually contained horrible bugs that have been fixed in 2010. So upgrade to 2010, please, especially if you're using regular expressions where they actually work like they're supposed to. And they're also faster. So here I've got sort of the hello world of a regular expression. Of course, I need to include the header regex, which is where all of the regular expression machinery is defined. I've also got my other headers. I'm going to be working on std strings. Now, one of the great things about the regex header is that the things in it are templates. We're going to be working with std regex, but this is actually a type def. For basic regex, of course, a namespace std of char. There's also a std_w regex that is a basic regex for wchar. This is just like how std_string is a type def for basic string of char, and std_w_string is a type def for basic string of wchar. My examples will only be using narrow characters because they're easy to use. But if you're working with Unicode, you should definitely be using the W forms of everything. There's helpful type defs. And not only is regex able to work with both narrow characters and wide characters, Unicode, it can also work with both std strings and const_char stars. So, of course, std string is wonderful, and you should be using it all the time. But sometimes you happen to have a const_char star, and you just like to directly match it. There's no reason to copy it into a std string just to use regex with it. Regex is not only templated on character type, but also string type. So its algorithms are templated on this. So they can work with std strings, they can work with const_char stars, const_wchar stars. They can even work with custom string types as long as they conform to the bidirectional iterator requirement. So basically any string you can possibly imagine, std regex will work with it. So here we've got the hello world example where I construct a regular expression, and this is going to contain something very simple, a, b plus c. What this means is this regex wants to match a single a followed by one or more b's, that's what the plus means, and then followed by a c. So I'm going to read strings from standard input that I type in. This is a quick little for loop to do that. And then I'm just going to simply match each string against my regex and print whether it matches or not. So let's compile and run this and see what happens. So I can type in strings like XYZ. That's not going to match. That's going to be false. I could type in ABC. So that conforms to the requirements. It's got one B. I want one or more, so this will be true. I could type A, B, 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 C, and that's also true. But if I don't have any B's whatsoever, that will be false because I asked for one or more. So if I just type AC, that will be false. Or if I have A, B, 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 C, C, I have too many C's. And this algorithm regex match requires that the whole input string match the whole regex. In this case, my regex matches a prefix of the input string, but not the whole thing. There's too many C's. So this will also be false. Oh, it's false. Now, if I wanted to change what kinds of strings are accepted, well, I can simply kill the program and go change my regex. So you'll notice that the only loop here is the loop that's reading in strings from standard input. The matching is performed entirely by regex. So if I want to change what's accepted, maybe I want to permit 0 or more B's and 1 or more C's, well, I can do that. recompile, and see what happens. So as before, XYZ, totally garbage, does not match. But if I have 0 B's and multiple C's, so like A, C, 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 that does match because I changed the regex. Of course, I don't need to construct a regular expression from a string literal in my source code, although that's a very common use for regular expressions. I could also read them from a data file. I could also read them from users, but you should be careful when doing that because users can type in sneaky things, especially if they're attackers. So you always got to remember security. String literals are sort of the simplest thing to use when constructing regular expressions, and so that's what I'll be using most of the time. So that is how to use regex match, which is sort of the simplest regex algorithm. But there's actually 3 that we're interested in. There's regex match, regex search, and regex replace. These are overloaded in a number of forms to work with std strings, stdw strings, or pairs of iterators. I'll only show you sort of the simplest versions. So we just saw the simplest possible use of one overload of regex match, and this asks, does the whole regex match the whole string? And it returns a yes or no answer. So this is good for validation, but sometimes we want more information. Sometimes we'd like to know what parts of the regex match what parts of the string. And this can be done through extra parameters to regex search. So suppose that I would like to describe a string. Maybe it's A, B plus, C plus, D. And I would like to match and ask, OK, how many B's matched and how many C's matched? So I can, in my loop, construct an object that will get the match results from regex match. And this is a class of type match results. But as usual, it's templated. And this one is templated on the string type. So I'm using std string, so I'm going to use the typedef smatch for a string match. There's also a cmatch if you're working with const stars, and then there's wide versions of these helper typedefs as well. So when I write smatch, that is a typedef for match results that works with narrow strings. So I will default construct 1. This is waiting for results to be filled in, and then I pass it as the second parameter to regex match. And now, if the match is successful, let me actually get that out here. Const bool b is regex match. So I will print whether it matched, and then if it matched, I can look at the smatch m and print m1 and m2. So what's going on here is that my regex has these parentheses. So parentheses serve a couple of purposes. The first thing that they do is enforce precedence. This is just sort of a regex syntax thing. If I wanted to write, I want to match either x or y, I use the pipe or the alternation operator. But what if I want to say I want to match a followed by either x or y followed by z? I can't write this because what happens here is that this alternation binds weaker than concatenation. What this regex means is match ax or yz. If I want to say match a and then an x or y and then a z, I need to wrap it in parentheses. So parentheses can enforce precedence, but they also do what's called capturing. And when I have a capture group or a subexpression in my regex, then I can ask later what matched this capture group. By the way, the grammar that I'm using here is referred to as, I'm missing a double quote. The grammar that I'm using is referred to as the ECMAScript grammar. ECMAScript is the standardization of JavaScript. So if you've used JavaScript regexes, you already know C++'s syntax. And it was also derived from Perl, which is an extremely popular regex syntax. And it doesn't have all of the latest features of, I think it's up to Perl 6 now. if you're familiar with regexes from Perl, you should feel right at home with this. The C++ regex also supports other forms of grammar, such as basic and extended POSIX regular expressions, grep, egrep. All of those grammars are horrible. You should never use them. They're limited and awkward to use. The only reason to ever use those grammars is if you must be compatible with some existing program that parses such regexes. Otherwise, use the default, which is ECMAScript, which supports all the features except for octal escapes of all of the other grammars supported. So let's go back to these capture groups. When I have my smatch and I have a successful match against a regex, when I write m bracket 1 bracket that says give me the substring that matched the first capture group, in this case it happens to be 1 indexed, m0 special, I'll show you what that is, and m2 is whatever matched the second capture group. So if I compile and run this, once again, if I type in nonsense like XYZ, I'll just get false and I won't be printing anything out from this match. But if I type something like A, B, 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 C, D, then I should expect to see, yes, it matched, and then B, 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 because that was the first capture group, and then C, which was the second capture group. And look, that's exactly what I get. So here I have both validated a string and then cracked it into its components. I could do things like match 1 or more digits and extract just a digit. In fact, why don't I do that? I can, I don't want to do that. Parse a date like this. I could say digit 2, another digit, and I'm going to want capture groups. Now, when I write \\d, I'll explain what that means in a second. And I've got a brace there, which I don't want. Parenthesis. Hey, that looks good. So I can do all this, cout m3, and OK. So here, when I'm writing \\d, that is special meaning. So the thing you have to remember is that when I write a regex in a string literal, it's first being parsed by C++. And we know that I can escape things for C++. So if I write something like x \n y \z double quote, these backslashes are for C++. They're saying, I want a new line in the string literal. I want an actual double quote in the string literal. That's all well and good, but sometimes we also want to escape things for regex. Regex processes the string, it's a library, after the C++ compiler gets to take a look at it. So if I want something like \d sent to regex, I need to escape that backslash for C++, which gets the first crack at it. So if I want to have a literal \d, I need to write \d in my string literal. C++ sees this and says, oh, 2 backslashes, you must want a single backslash in your string literal. And then regex sees, oh, \d, great, that's exactly what I want. So you need these double backslashes whenever you're writing regular expressions in string literals. Of course, if you're parsing them from a text file, then you don't need that. C++ OX has a feature called raw string literals that allows you to avoid this sort of thing, but it's not implemented yet in VC10. So right now, I've got to write these double backslashes. And what \d means is I want to match any digit. There's another way to write this. I could write, I want a class, all the digits from 0 through 9 inclusive, but writing this compared to \d or double \d, this is actually shorter and a little easier to understand. Of course, they're equivalent, but I always prefer using the escapes when I can. And the other thing I'm using here is a quantifier. There are quantifiers star, and that means 0 or more. There's plus, which means 1 or more. There's also question mark, which means 0 or 1. If I want an exact count, like I want 4 digits, I can write that in braces. So if I say brace for brace, well, that means exactly 4. I can also put ranges here, so I could say I want 3 to 4 quantities of this. So here I've described a date, and I can crack this open and run it. So if I type in something like 1105, I've required 2 digits, and then 2010, look there. I have parse the state into 3 components, the month, the day, and the year. At this point, the regex doesn't care what it's matching. It doesn't care if the month is that first couple digits or the second couple of digits, and it'll accept anything that conforms. So I've said, okay, I want exactly 2 digits, but I didn't say that it has to fall between 0 and 31. So I could type in something like 99/55/1234, and this will be accepted by the regex. So the regex can only look at strings. I could get more clever and permit 0 or 1 digits for the month and the day. But if I want to actually parse it as a number, I'll need to convert that into a number, perhaps using the functions toString and s2i added in VC10. And then test, okay, is this number less than 12, less than 13? Is it falling within the range of days acceptable for that month, and so on. But the regex will at least allow you to split the string into its components. So that is capture groups. So let me kill this. And that's regex match. But what if, I had mentioned M of 0. And we'll see that with regex search. With regex match, the 0th capture is not so interesting. So regex match asks whole regex match whole string. What regex search asks is, I've got a regex, does it match some substring? So if I have the string A, B, C, 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 D, 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 E, 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 F, G, and I have a regex C plus, this is the string S, this is the regex R, C plus, D plus, E plus, then regex match will say, hey, this regex does not match this whole string. There's this other stuff, AB and FG on the outside, doesn't match. Regex search asks, does this regex match any substring of my target string? And the answer here is yes, it does match this. So let's see what that looks like. Otherwise, regex match and regex search have exactly the same parameters and behavior. So let us go here, and I say C plus D plus E plus. And right now I won't be using the, well, I can, I'll immediately start looking at this match. If I wasn't interested in the match results, I could omit this M parameter just like I did before. And why don't we print M of 0 and get rid of these other guys. And now, instead of regex match, I want regex search. And compile and run. So as usual, XYZ doesn't search, so false. Now if I type something like A, B, C, 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 D, 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 E, 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 F, G, regex search will say, yes, I found an occurrence of your regex in here, and so it prints true, and it prints out what matched. So when you ask for the 0th capture group, that asks for the whole part of the string that matched the regex. So in the case of regex match, this is never interesting, because you know that the whole regex had to match the whole string in order for it to return true. But in the case of regex search, because it can match a substring, looking at M of 0 can be very enlightening. And in this case, I got what matched. Now, you might ask, okay, well, what happens if there are multiple occurrences of my target pattern in the string? So if I write A, B, C, D, E, F, G, well, I put a couple capital X's there, and then C, C, D, D, E, E, like this, I now have 2 occurrences of my desired pattern in my target string. Which one will regex search return? Well, if you've seen the other ESTA algorithms, you'll probably be expecting the first match to be returned. And in fact, that is exactly what you'll get. In this case, I got true, and it printed out, okay, what matched CDE? So regex search will return you the first occurrence of whatever you're looking for. If you want to look at all occurrences, that's where regex iterator comes in. Now, here's a warning. You may be tempted, if you want to look at all occurrences of a pattern in a string, to call regex search over and over with an iterator into your string that you step forward every time you find a match. Never, ever do that. There are reasons why it's bad, as explained in my slide deck and Pete Becker's TR1 book. Sort of the brief explanation is that if your regular expression contains things like anchors, so if you write a hat and a dollar, This means match the beginning of the string, match the end of the string, or you can have word boundary anchors like I want the boundary of a word. If you ever call regex search repeatedly, you can interfere with how these anchors work because every regex search call believes that it's being given the whole string. The other thing you can do is imagine that your regex could possibly match 0 characters. So if I write something like A star or B plus, well, this will match 0 occurrences of A or 0 more occurrences of A or 1 or more occurrences of B. If this can ever match 0 characters and you're calling regex search in a loop, congratulations, you have an infinite loop in your program. That is awesome. Not. Whereas if you use regex iterator, your program will never infinitely loop because it's smart and it knows what to do if a 0 length match is ever spit out. So regex search is useful, but never call it in a loop incrementing an iterator forwards. So now, one of the things you might be asking is, okay, we can do match, we can do search, we can ask what matched, but you're only printing out the contents of the string. What if I want to know exactly where, in terms of iterators or indices, something matched? Well, this information is actually being returned, and we can look at it. So we've seen here that you take your input string and your input regex, and you feed them into your regex algorithm, one of these. So for example, regex search. You can also feed in a match results. Like the typedef smatch, and get information out of it. So here I can ask something like m of 0 for the whole match. What this actually is, it looks like a string, and it's convertible to a string. So I can cout it, I can push it back into a vector string, but it's actually not a string. What it is, it's a submatch. Again, this is templated, there are typedefs. This one happens to be an S submatch because it's for strings. And what it actually is, this is a class that is derived from a pair of iterators. In the case of S submatch, it's derived from a pair of string const iterators. In the case of a C submatch, it's a pair of const-char stars. And what submatch does is it adds another member called matched. You can ask, okay, did this submatch participate in this match with the regular expression? And it also adds conversions, so you can convert this to a string. You can also ask for .stir to explicitly request a string. And of course, because it derives from pair, you can ask for .first and .second. This is how to get the information, where did my submatch occur in the target string, not just what does it contain. So let's see that in action. I can ask for m0.first, and this is an iterator to my string. If I want to know the index where it occurred, well, I can subtract my string s, begin, and I can get the same thing for the end. Which would be second. And compile and run. So there we go. Now, if I type in something like XX, and I'm looking for C, D, E, Y, Y, and then C, D, E, Z, Z, then here it prints out true, and it prints out 2 and 8. Because if I have X, X, C, C, D, D, E, E, Y, Y, and then other stuff, I don't really care what that contains, then this is index 0, 1, 2, 5, 6, 7, 8. So I printed out 2 and 8, meaning that, hey, this is where the match began, and this is where the match ends. Of course, regex is using the STL's inclusive, exclusive bounds as usual. So that's why I get this range. So then I can look at that string by doing .stir, or I can work on it in place. Now, if you're ahead of me, you'll have noticed what this is doing. Not only is this very convenient in that it can give me the string that matched, and it also can tell me where the string matched. It is conserving space. Submatch is constant space. It's just a pair of iterators, whether consecutive stars or string iterators. It doesn't matter how big that substring is. The submatch, which is contained within this match results, is constant space. So you can work on insanely huge strings, megabytes long, and your submatches will be very tiny because they only have iterators into the original string. Of course, if you ask for .stir, it's got to go copy whatever substring you're referring to. But if you just want to work on it in place, submatch will work just fine for you. Finally, I'd mentioned regex replace. Let's look at that in action. So if I have something like this, I can say, let me put a format out here. String format. Let's pick a string completely at random. And then inside here, I want to regex replace. Come on. And I seem to have lost a brace. There we go. So what this is saying is I want to look for every occurrence of one or more C's, one or more D's, one or more E's, replace them with the string meow, and print that out. So regex replace will return a new copy of the string with every occurrence by default of my target pattern replaced. So if I compile and run this, what I'll get, if I have something like XX, CDE, YY, CC, let me put some more Y's in there, CC, D, EEE, I should expect to see both of these occurrences of my pattern replaced. But if I have anything else, like maybe CE, and then this does not match because I had asked for one or more. So anything that doesn't match will be left unmodified. And look, the patterns that I want were replaced, and the rest of the string was copied unmodified. Now there's extra flags that you can pass in to regex replace asking, I want you to replace only the things that matched, and anything that did not match, I just want you to drop on the floor. That's called format no copy, I believe. And that can be very useful when you want it, but by default, everything is retained that didn't match, and all occurrences are replaced. You can also ask for just the first occurrence. If you're familiar with Perl, this is very much like its S/ syntax. So in Perl, you can ask for replace target pattern with the new string or format string in this case, and then you can ask for global, which means replace all occurrences. What regex replace is doing is this is just on by default, but you can turn it off. But you have to call it with parameters like this because C++ regex doesn't interpret this Perl syntax. I'm simply showing you for the purposes of explanation. You can also refer to the original regex. For example, if I have a capture group, I can use that in my replacement. So for example, if I have my D's captured like here, actually, why don't I show you something even a little more interesting. Maybe I captured all of these. I can replace with something like this. $3, $2, $1. So what this syntax means in the format, when I have a dollar and then a number, this refers to the nth capture group, very much like my match results. And it says, I want you to replace whatever matched the nth capture group here. Of course, you can escape the dollar itself with a double dollar. You can also ask for the prefix and suffix of what matched. So if I compile and run this, and I pass it something like AA, CC, D, EEE, BB, I won't show you the multiple occurrences. What happened here is that it matched the C plus D plus E plus, and then stored what matched each capture group, and then my format string was able to juggle these sub-expressions around and add extra bits there, like square brackets and dashes and whatever else I wanted. I could also drop some of the capture groups on the floor if I wanted to remove that from my string, or I could replicate them. I could say $2, $2 to get a couple occurrences, whatever I like. And of course I can load these format strings at runtime if I want. They don't have to be string literal. So here you should be seeing how powerful regex replace is. Finally, let me show you how regex iterators work, since I had mentioned that. Let's stick with C plus D plus E plus, but I don't need a format. And now, what I want to do is I want to do for regex iterator. Oh, the other thing that I mentioned, forgot to mention, is that these regular expressions, what are they? Well, it's very tempting to think of a regular expression as a string because that's what you construct it from. But in fact, if you have a regex object, what it is, it's a pointer to a non-deterministic finite automaton, which if you've taken CS classes, you've probably seen in like CS 102. And this is, you can think of it as a bunch of dynamically allocated nodes that do something tricky. This is how it matches arbitrary strings efficiently. And it's a complicated data structure. Constructing a regex takes time. So you don't want to be constructing temporary regexes if you can avoid it. That's why I've constructed my regex once and then used it over and over. The other thing is that things like regex iterator and whatever, they need to actually point to, if I've got a regex iterator, my regex iterator will store just a pointer internally to my regular expression data structure. So I cannot construct a regex iterator with a temporary regex because that temporary regex will be destroyed as soon as I hit a semicolon, and my regex iterator will be left with a pointer to garbage. So both for efficiency and for correctness, always give your regular expression names. Temporary regexes are something you basically never want. So I'm going to construct a regex iterator. I'm going to call it I. And this needs to store a couple iterators into the source string. So I need to pass it sBegin, sEnd. It wants the regex. It's going to store a pointer to this regex. And then I need an end iterator. So if you are familiar with how iterators work, you know that if I am iterating through a vector, I always need to say vBegin, vEnd. I need to ask for the vector's end. What I can't do with any standard container is say, oh, I just want a vector int iterator. Maybe call it E. If I default construct an iterator, that iterator is called singular. It means it contains garbage and it's completely useless. You can't compare it to anything, certainly can't dereference it, can't do anything with it other than destroy or assign it. So with container iterators, you always need to ask the parent container, okay, what's your end? However, some iterators have special guarantees. iStream iterator behaves like this, and so does regex iterator. So if I default construct a regular expression iterator, that is the end of stream iterator. So I don't, because there is no parent container to ask, I don't need to somehow ask my regex, okay, give me a .end. I simply default construct a regex iterator, and that is the end iterator. So I'll just construct a iterator here, like this, and then I can repeatedly use it as long as I doesn't equal end plus si. But this is a special guarantee only for regex iterator and regex token iterator. Don't assume it by default for arbitrary iterators you run into. So when I dereference a regex iterator, what I get is a match results. We've seen how that works. So if I dereference I, I've got a match results. We know it supports operator bracket bracket to look at capture groups. So I could look at just the second capture group. I won't print out everything. And here we know that the submatch, which is deref I of 2, is derived from a pair of iterators. So I could look at its .first, .second. You see how all the pieces are fitting together. Here I'm just going to convert it into a string and print it out. This. Compile, run, and should be good. Oh, I got something wrong. Oh, yes. Ha! Regex iterator, again, it's a template. Templated on string type and character type. I want the helper type def s regex iterator because I'm working with std strings. There we go. And hey, that red squiggle disappeared. I should not ignore that stuff. Compile and run. Ding. Okay, so now if I have a string with multiple occurrences of my target pattern, so AA, C, D, D, E, 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 B, B, C, 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 D, D, E, something like this, then my regex iterator will step through every occurrence of my target pattern in the string and give me a match results to look at. So I can ask, okay, not just you matched, but where did you match and where did your captcha groups match? So if I print this out, then I get each of the second captcha groups, the D's that match. In this case, they were the same. Let me make them different. C, D, 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 E, E, B, B. Here I expect to see many D's printed and then just one D because I'm iterating left to right. That's exactly what I get. So regex iterator is the way to ask, okay, I want to look at all of the occurrences of a regex in a string. This is enormously powerful. The last iterator, which I won't go into detail to in this talk, but you can look at in the slides, and of course on MSD and documentation or Pete Becker's TR1 book, is regex token iterator, which is an adapter over regex iterator itself. And what it can do is say, okay, instead of iterating through every occurrence of this whole regex in the string, I want to look at just captcha groups 1 and 4. So every occurrence of that regex, I want to see captcha group 1, captcha group 4, captcha group 1, captcha group 4, and so on. Maybe the other captcha groups, I don't care what they contain. Or if you pass the special index -1 to it, it can do something enormously powerful. It can say, okay, I'm going to describe some part of my string that I don't care about. Maybe it's white space, maybe it's punctuation, maybe it's parentheses, whatever. I want to iterate through all substrings that aren't this bad thing that I don't want to look at. This is tokenization, where you're breaking the string into tokens separated by white space or whatever you're describing. This is the generalized form that I mentioned of strtoke. So that is a quick introduction to the regular expression library that has been added to the C++ standard. There are many things that you can do with it. I've only scratched the surface. Take a look at your code and see if you're working on any strings with handwritten iterators or maybe even STL algorithms. If you can describe them with regular expressions, that's even better because you're offloading the work of matching the string and replacing stuff to regex. Not only is it likely to be more efficient, it is much more likely to be correct because manipulating pointers and iterators by hand and doing detailed work is a bug farm. We all know it. And the other thing is that even if your handwritten code is correct, it can be difficult to change. Whereas we've seen with regex that if I want to change what I'm matching or what I'm replacing, then I only have to modify a couple of strings. Because it's declarative, I simply describe what I want and the regex header gives it to me. So take a look, see if you can simplify your code. See you next time.